Have you ever wondered how a self-driving car determines which path to take, or how a chess engine determines what's the next best move? Behind these smart decisions lie powerful search techniques in AI. I'm Arushi Iyer from VisionGATE, and today I'll be introducing you to the basics of search techniques. Before diving into specific algorithms, let's understand what an agent is and how it approaches problem solving. An agent is an entity that perceives its environment through sensors and acts upon said environment through actuators based on a decision-making process. In a search problem, the agent will perceive the initial state of the environment. It will have access to a set of actions or operators. Each of these actions will lead us to a new state defined by the transition model, which will tell the agent how the world changes when an action is performed. The agent also needs a goal test function to check whether it has reached the desired outcome or goal state. Since there can be multiple ways to reach a goal, we often use a path cost function to evaluate how efficient a solution is. And this is measured typically in terms of either time complexity or space complexity. Take a look at the diagram on your right. We have one initial state and two goal states. There are multiple ways for us to reach from the initial state to the goal states. There's one path that goes through nodes A and B, another going through nodes C and D, and another going through the nodes C, D, and F. To determine which path leads to the most optimal result, we need this path cost function, because this is the function that will help us compare the different paths based on their total cost. Now let's take a specific example of the 8 puzzle problem. This puzzle consists of a 3x3 grid with numbered tiles from 1 to 8 and a blank space. You'll be given an initial configuration like the one you see on your left, and the goal is to reach the final configuration like the one you see on your right. The final configuration will be the same 3x3 grid with the blank occupying the first tile and the numbers 1 through 8 sorted top to bottom, left to right. The 8 puzzle problem can be represented in the form of a search tree, where the initial state S is the starting configuration. This can be our root node, and the successor states are generated by making valid moves, like sliding the blank space either up, down, left, or right. Each branch in the tree will represent a possible move. So the root node is represented by the initial state. The nodes will be represented by the states that we get by making moves or actions represented by the branches. So the new nodes that are generated are called frontier nodes because they lie at the edge of the expanding search space. The frontier nodes are also called the open list. The 8 puzzle problem is an example of one search problem, but there can be many such problems which can be mapped to a search tree. So the tree search algorithm offers a general framework to represent and solve such problems by modeling states as nodes and actions as edges. So let's take a look at the algorithm itself. Let S represent the start state, G represent the set of goal states, and the open list represent the frontier nodes. We initialize the open list to contain just the initial state or the start state. If at any point during the exploration, the open list is empty, it means that we don't have any other nodes to explore. But it also means that we weren't able to find a path from the start state to the goal state, which is why we terminate with failure. If that is not the case, the open list will have at least one node. So we will select this node or state n from the open list. Now we will check whether this state is one of the goal states. If it is one of the goal states, we have found a path from the initial state to a goal state, so we can terminate with success. But in the case that it is not a goal node, we will have to expand and generate its successors so that eventually we may reach a goal node. So the expansion step consists of generating the successors of n and inserting them in the open list. Generating successors simply means applying all the valid moves on the current state n. After generating the successors of n, we can simply go to step 2, which is again checking for the open list. So this is the tree search algorithm. The tree search algorithm seems quite straightforward at first, but I want you to pause and think about this carefully. If there exists a path from the initial state to one of the goal states, does the tree search algorithm guarantee that we'll find it? Before you jump to an answer, here's something important I want you to note. This algorithm does not remember which nodes it has already expanded. That means that in step 5, when we generate new nodes and add them to the open list, it's entirely possible that some of these nodes were already generated earlier. But since we're not keeping a track of them, the algorithm can end up re-exploring those same nodes and all of their successor paths again, leading to unnecessary repetition. So the answer is no. We are not guaranteed to find a solution. Now let's try to understand this better with the help of an example. Suppose our initial state is S. After moving right, we will be reaching state A. Now we've already checked both S and A and we know that they are not the goal states. However, if the algorithm doesn't remember the visited states, A might again move left, taking us right back to S. So this can lead to an infinite loop, which will waste time and computation. So how do we avoid this? We can enhance our approach by keeping track of the visited nodes. In addition to the open set, which will hold the nodes that are yet to be explored, we can also maintain something known as the closed list or the explored set, which will record states that have already been visited. So if we augment the tree search with the explored set, we get what is known as the graph search algorithm. So let's take a look at the graph search algorithm now. This algorithm is very similar to the tree search algorithm with two key improvements. One, when a node is selected from the open list, we will add it to the closed list. Here, in the select state, when we select a state n from the open list, we are also going to save it in the closed list. And second, while expanding the node, when we generate the successors of n, for each successor m of n, we will insert it in the open set only if it has not been explored yet at all. So we will check if it is neither present in open nor present in closed. Because if it is already present in the closed list, it means that the state is already explored and there is no need to waste time going down a path that we've already seen. And if it is already part of the open list, it's waiting to be explored and we don't need to add it again, otherwise we'll end up with duplicates. So this simple enhancement helps avoid unnecessary repetition and improves efficiency. The open set itself can be implemented using different data structures, such as a FIFO queue for breadth first search, LIFO stack for depth first search, or a priority queue for informed search algorithms. The graph search algorithm, as we saw, helped us by avoiding revisiting states that have already been explored. But here's a key question. If a path exists from the initial state to one of the goal states, can a graph search algorithm always guarantee that we'll find it? We'll dive into this question in the upcoming videos. Along the way, we'll also explore a variety of search techniques, both uninformed and informed, and we'll evaluate them using key performance metrics. We'll also walk through examples to build an intuitive understanding. That's all for this video. Thank you so much for watching. If you found this helpful, don't forget to like, comment, share, and subscribe to the VisionGATE channel for more content on computer science and data science subjects. See you in the next one.